Okay, we have just a little bit to sort of wrap up in terms of molecular polarity and bonding. Uh, but last time in chapter 4 here, we got into obviously, actually, we did that before. I think we did our geometry, but we really got into hybridization. And remember, hybridization is basically linked to electron pair geometry. So basically, the number of electron pairs, you count it just like you would do geometry. So if you have two, that essentially is sp hybridization. And the easy way to count off sort of hybridization is to basically just kind of delist, mark it off. So two basically means 1, 2, and that would give you sp hybridization, which goes with our linear geometry. Three electron pairs will give you 1, 2, and one more makes 3 sp2 hybridization. That goes with our trigonal planar electron pair geometry. Four electron pairs, 1, 2, 3, add one more, there's 4. That's an S and 3 Ps, and that will be tetrahedral. It also can account for the expanded octet, where we have, say, 5 electron pairs. Adding one more there gets us sp3 dehybridization, and that goes for our triangular bipyramidal. And lastly, we could also have 6, which is our expanded octet. Add one more to the list there, and that is sp3 and a couple of Ds there happening, and that is our octahedral geometry. So hybridization can pretty much just be counted like you're counting electron pairs. You could apply hybridization, as we talked about, to central atoms. You could also apply it to outside atoms. Really, typically speaking, we just don't apply hybridization to hydrogen because it has one electron, so it can't really promote it up and all that kind of situation that could occur. We also talked about how sort of bonds come together. So pretty much kind of like your single bond or your first sort of bond is usually a sigma bond, and that's head-to-head overlap of those orbitals. And that's different than how we get sort of to a double bond or a triple bond. In a double bond or triple bond, the double bond here, the first bond is that sigma bond. The second bond is a pi bond. Single bond, just a sigma. Pi bond is a result, as we talked about, of those unhybridized p orbitals, again, doing sideways overlap, and that is what accounts for sort of that pi bond that occurs. Again, with a triple bond, kind of works the same way. We have a single bond, a sigma bond, and we actually will have two pi bonds happening. And that also is, both of these are from unhybridized p orbitals, again, doing that sideways overlap. So when we go through hybridization, especially say sp2 or sp hybridization, thank you, we will end up with some unhybridized p orbitals, and it's those electrons that are in those unhybridized p orbitals that are going to be used to make kind of like your second bond in your double bond, your third bond in your triple bond along the way. We talked about at the very end there molecular polarity as well. And again, a reminder that molecular polarity is a sense different than bond polarity. Again, bond polarity is typically where we use that difference in electronegativity values to determine whether or not the bond between these two atoms are going to be polar or nonpolar. The only place where, again, as we talked about, these two pretty much will actually be the same thing is when you have, again, a diatomic molecule. And when you have a diatomic molecule, because it only has one bond, pretty much whatever that bond is, if it's a polar bond or a nonpolar bond, will be pretty much what the molecule will be, either polar or nonpolar, because pretty much that molecule is only made up of one bond. So that pretty much will determine, what it is. If you do have a polar molecule overall, it will possess what is referred to as a dipole moment. That dipole moment is drawn with the same type of arrow that we've used for bond dipoles, where it points to the more negative side of the actual molecule, and the guy that kind of makes a plus sign is to the more positive side of the molecule in this particular case. Nonpolar molecules will not possess a dipole moment. So if the molecule is nonpolar, it will not possess a dipole moment. Now, when we look at something like we looked at there towards the end, like CO2, it does possess, again here, polar bonds with the oxygen being more electronegative. So we can draw our bond dipole arrows here, and it definitely has polar bonds. Remember that when you move away from the diatomic molecules, you have to actually look at a couple of things. And when you have three or more atoms involved, you got to determine, are there polar bonds? And you also have to look at the molecular geometry or the shape of the molecule. So as we talked about last time, the shape of this molecule is linear, which means it's basically a straight line. And that means that because of the geometry here, these bond dipoles, which are really vectors, are going to be pulling in equal and opposite directions, like on a rope, and nobody's going anywhere in that situation. They're going to actually cancel each other out. And that will mean that this guy would actually be a nonpolar molecule. It would not possess a dipole moment, as we talked about last time, because of that. It's also a really good example of a molecule that can definitely have polar bonds, but again, because of its geometry overall, it will be able to kind of share those electrons equally and become a nonpolar molecule, which basically means, just like it does when we have a nonpolar bond, if you have a nonpolar molecule, it is essentially a neutral molecule. There is no like negative side or positive side of that molecule. All the electron densities sort of spread out equally over it, and we don't get this kind of buildup of negative charge on one side of the molecule versus the other. Now, we also looked at water, which is also a classic example of a polar molecule. And once again, this also has bond dipoles or polar bonds. Because this geometry is bent or V-shaped, what ends up happening is these two vectors actually will add to one another, and you'll get a net dipole moment heading in this direction when they do so through here because of its geometry. Whereas we talked about last time, the oxygen part is going to be more negative in water. The hydrogen part of water is going to be more positive. And this would be its dipole moment I drew right there through the center, would be its dipole moment. And this would be a polar molecule. Any questions on that stuff we talked about last time there? I think that's where he kind of laid up, I think. So where we laid up was, I was just about to tell you, nobody wants to do vectors and figuring out if they're going to add to each other or cancel each other out. So there really is sort of a quick way that you could kind of do molecular polarity. And probably I would say 97, 98% of the time, maybe even higher, you'll probably be correct if you just sort of follow this. And that has to do with geometries. There are actually, we'll do this. We'll start symmetrical. There are symmetrical geometries. And the geometries we're actually talking about here are the molecular geometries, or the shape. So some of the symmetrical geometries that we talked about are, try to remember, we got trigonal, planar, and again, this is molecular geometries. We have tetrahedral. Uh, you got triangular, bipyramidal. You got octahedral as well. And what all of these basically have in common is if you draw the Lewis structures for these guys, you will have no dots on the central atom, which really means that you have no lone pairs there on the central atom. And if you have this geometry, these are going to be symmetrical geometries, which means everybody's just going to line up kind of perfectly equal to each other. And if all the atoms are on the outside, all the atoms on the outside, there we go, are the same element, you will get a nonpolar molecule. And that is because you'll have all the same elements on the outside. They're all going to pull equally, and they're all basically arranged equal distance from each other or in equal and opposite directions. So it's going to be, again, like everybody pulling on the sort of rope equally in opposite directions. They will cancel each other out, and you'll end up with a nonpolar molecule. Now, there is an exception. For example, though, if we looked at, say, this guy here, if I can make that thing an F, there we go. We'll do this guy here. So when we look at this one here, does it have polar bonds? The bond between carbon and fluorine, is it polar? I should hope so. Fluorine is the most electronegative element there is, and they're sitting in the same row on the periodic table. So we definitely have polar bonds happening here, all pointing towards the fluorine. But because of the geometry here, they're all going to cancel each other out because is a symmetrical geometry. So if I look at this, really all I have to look at is there are no dots. Everything on the outside is the same. It's going to be a nonpolar molecule. So once again, even though it does have polar bonds because of that symmetrical geometry, it's like everybody in the corner of the tetrahedral pulling on a rope equally. Nobody's going anywhere in that particular case. Now, there is a sort of exception to this quick symmetrical rule, which is if I take something like this, for example, also with my fluorines, and I swap out one of my fluorines for, say, hydrogen in this case, I still have my polar bonds happening, right? But now I have a carbon-hydrogen bond, which is actually nonpolar, right? And in this case, even though I do not have dots on the central atom, all the outside atoms are not the same, right? We're actually going to get these three guys pulling, and this guy is frankly not really going to pull back the other way. He's actually going to help a little bit going in that direction, to be honest with you, towards the carbon. And you can kind of imagine in that case, right, three of the four people pulling on the string. That fourth guy is going to come for the ride, right? He's not going to be able to hold on. And this will now become a polar molecule. So if you draw a Lewis structure and you have one of these symmetrical geometries where you look at the central atom, there's no dots on it, which means there's no lone pairs, and you have all the same elements on the outside, going to be a nonpolar molecule, pretty safe bet. If you draw a Lewis structure in one of these symmetrical geometries and you have no dots on the central atom and all the atoms on the outside are not the same, also probably a pretty safe bet it's going to be a polar molecule. So that is like how you can do it like in a super quick way. No dots, everything the same, non-polar. No dots, everything's not the same, going to be polar. That also leaves us, though, some unsymmetrical geometries. So we do have some unsymmetrical geometries. And again, these are our molecular geometries. You got those expanded octets, so you got a big list. So let me see if I can remember the list here. So you got, we got our angular We have our trigonal pyramid. We have our bent or V-shaped. We have our T shape. We have our seesaw, right? We have our square pyramidal. Feel like I got them all, hopefully. So these are the guys where if you draw the Lewis structure, you will have dots on the central atom. So if you draw that Lewis structure, you got some dots on the central atom. And when you look at the outside atoms, if they are the same element, you will most likely have a polar molecule because you're going to have an unsymmetrical geometry happening. That's the case like we saw with water. I see dots. I see the same thing on the outside. It's going to be a polar molecule. So if you have dots, you have everything the same on the outside, it is going to be probably polar. And that's, again, a pretty safe bet. Nothing's 100%, but pretty close to doing that. What does that leave you in terms of geometry? It actually leaves you a couple here that I did not put on for unsymmetrical geometry, and that is because they actually should go over here. And there is a couple of exceptions to the no dot rule here, and those are the linear geometry, and this is the expanded octet linear, not the normal linear, if you will. That's the one that looks like this. This linear here, basically. This linear here, if you have that geometry and everything on the outside is the same because it's linear, it's going to cancel out because they're going to be pulling opposites of each other or pushing. And these guys here, the non-bonding electrons, make a nice perfect triangle and they're going to cancel each other out. So this is one exception where you could have dots on the central atom and still be non-polar if you have all the same things on the outside. The other exception where you could have dots on the central atom and still be nonpolar is our square planar. That's also our expanded octet. And that looks something like this. Why? And that is because, frankly, you make a square, which means if they're all the same on the outside, everybody in the corner of the square is going to be pulling towards each other, and they're going to cancel each other out. The two non-bonding electrons will go opposite of each other and not really be at play either. So these are two exceptions where, again, you could have dots on the central atom and end up being nonpolar. But pretty much outside of those two, if you have dots on the central atom, it's probably going to be a polar molecule if everything on the outside is the same. Any questions on that? What that really does leave you in terms of what you might have to actually figure out is really just the real linear, just the basic two electron pairs, two bond linear. And that one's pretty straightforward because, frankly, it's a straight line. So as we talked about yesterday, if they're going in equal and opposite directions, it's going to be nonpolar. If it is linear and they are heading at each other, equal and opposite, is going to be nonpolar as well. So both of those would result in a nonpolar situation. Now, if you did have something where maybe everybody was heading in the same direction, then you would have a polar molecule. So linear is really the only one you have to probably truly worry about. And I would say the regular linear, and again, that's pretty straightforward. Like I just said there, you can pretty much just, they all heading in opposite directions. They all heading in the same directions. So really, dots, no dots, you could probably figure out molecular polarity in like 5 seconds every time you look at it as you draw a Lewis structure. So let's take a look here. This is one we talked about here, HCl, which obviously is a diatomic molecule, has a polar bond, which means the molecule is also going to be polar and will have a net dipole moment, which would be that guy right there. Here's our CO2, where obviously they would cancel out, as we've talked about. There's our water, where they will add together, again, giving us our net dipole moment, as we talked about. Here is NH3, right? So if I draw NH3, when I look at NH3's Lewis structure, what do I see on the central atom? I see dots. I see everything on the outside is the same, polar or nonpolar. Gonna be polar, yeah? It's gonna be a polar molecule. Dots, everybody on the outside is the same. It's gonna be definitely polar. As you can see here, that is the net dipole moment happening there in NH3. It's actually more negative towards the nitrogen, more positive towards the hydrogen in this particular case. So what is the effect of polarity or molecular polarity on molecules? The effect of it is it has a lot to do with solubility. There's this idea, as we will talk about in a later chapter, of like dissolves like. And the idea there is if you have a polar molecule, it will mix perfectly with another polar molecule because they're both using basically the same type of force. If you have an ionic guy, it will actually also mix well with a polar molecule because they both have charges, basically, right? Positive, negative sides. Also, if you have nonpolar molecule and a nonpolar molecule, they will also mix really well because they're basically the same. It's only when you cross over to polar and nonpolar molecules that you will run into trouble. They are not going to mix. And that's what we see here. There's water, which is polar. There is oil, which is nonpolar for sure. And as you can see, no mixing happening there. They will definitely separate out from each other. And as we'll talk about in a later chapter, they have no way to like maintain any type of interaction over a long period of time. Can they do it for a very short period of time? They can, hence the oil and vinegar salad dressing, right? You can mix it. It will stay mixed for a bit. But as soon as you put the bottle on the table, eventually what happens is everything starts settling out from each other, right? They can't maintain that mixture basically over the long period of time because they're very different. This is basically soap, in case you're curious. Soap has two parts to it. That is a nonpolar, what is referred to as the nonpolar tail of soap. This is, actually I went too far there. That's actually the nonpolar there before that part. Got a little carried away with my line there. There you go. So that is the nonpolar part right there. This part here is actually the polar head of soap. And soap works really well because most dirt is nonpolar, which means when you put soap on it, this nonpolar part back here will mix really well with the dirt. My squiggly line is this back part here, the nonpolar part of it. So it'll mix really well and it'll trap your dirt in what's known as a micelle. What it will also do is because this part of it is playing with dirt, this part now lines itself on the outside, which is the polar part of soap. And usually when you use soap, what do you use to wash it off with? Water, I hope, right? Usually, I imagine, right? So usually you go and wash your soap off with water, which works really well because now all the polar part of soap is on the outside. You come in with your polar water to wash it off. It has the dirt trapped in the middle on the nonpolar side. Out goes the dirt with the water, right? As you wash it off, that's how soap works. These are life lessons that are good to know, I suppose, right? Now, when we look at these two here, we want to decide, are these going to be polar or nonpolar? Plus, I'm going to add a couple other ones that maybe we looked at earlier. So let us take a look at these. And what we want to know is, are these guys going to be polar molecules or non-polar molecules? So let me just add a couple here that maybe we drew earlier. 2 minus, and we'll do this guy here. Oh, that's good. All right, so for each of these molecules, are they going to be polar, non-polar? Take a moment and decide. Want to take a look just to make sure that you do have some polar bonds, right? Otherwise, that would probably be not so good. Even if you didn't have polar bonds, it still would probably be unsymmetrical and still be a polar molecule. But let's take a look. We have nitrogen, oxygen, difference in electronegativity about 0.5, which means we do have a polar bond heading in that direction there. Badly drawn arrow. Nitrogen and chlorine is actually non-polar, right? Difference in electronegativity is 0. They have that diagonal relationship happening that we talked about. Geometry here is angular, which means this guy is kind of heading like in this direction. And basically here we have this guy basically just pulling down on one side, right? So you can imagine if we did that, the whole thing's going to fly. And it will have probably a net dipole moment heading kind of in that direction towards the oxygen in that case. So this guy would be polar, this molecule here. Here, we don't really have to worry too much about anything here because when I look at central atom, I see no dots, right? Everything on the outside is the same. That's going to be a non-polar molecule. Even though, again, here, sulfur and oxygen, it has polar bonds in this case. But because of its geometry, it's going to be trigonal planar, right? Which is a triangle. And you basically have everybody at corners of the triangle pulling equally. They're going to cancel each other out. Again, you can just do the quick version of it, right? Any question on those two? All right, now we're going to roll with the quick version. Here, polar or non-polar, this guy. It is going to be polar. I got dots. Everything's the same. Polar. Polar or non-polar, this one. Non-polar, no dots. Everything's the same. Non-polar. Polar or non-polar? It is non-polar. No dots. Everything's the same, right? Polar or non-polar? Polar, dots. Everything's the same, right? Polar or non-polar? It is non-polar, diatomic, right? They cancel each other out. How about over here? This is actually polar. This one you do have to look because the geometry here is actually regular old linear, right? And here we have a non-polar bond, right, between carbon and hydrogen. And we do have a polar bond going this way, right? So basically everybody's pulling to the right, like just one guy pulling on the rope on the right, nobody pulling back the other way. It's going to move. So this would be polar with a dipole moment heading in that direction. By the way, obviously here we'd have some dipole moments heading in that direction. And kind of the same thing if we drew the SO2 like this, we would have it heading towards the oxygen because it's angular basically. So that's really the quick way. As you can see, you can pretty much do molecular polarity in like 5 seconds. Your dots or no dots. You just got to watch out for, in your case, for expanded octets that do have dots that could be nonpolar. And again, it's just those two you have to worry about: the expanded linear and the expanded square square planar. Any questions on that there? All right. That wraps up this chapter, I think. We talked CO2 into the ground, I think. So there it is. All right. We're going to wrap up here chapter 4. We're going to go back to chapter 3 now and talk about some nomenclature. So we're going to talk about nomenclature and how to name everything so you will be professionals. If you're not professionals already, you'll be professional namers, I suppose. So this is nomenclature, and we're going to talk about really naming the 2 types of bonding that we've been talking about, which is ionic bonding, which obviously, as we hopefully know at this point, is between a metal and a non-metal. And whenever we get a metal and a non-metal together, we are going to get a transfer of electrons. And the result of that, as we talked about, will result in a cation being formed that's positively charged, and from our nonmetal, an anion that is formed, which will be negatively charged. That's going to yield an electrostatic attraction. Opposites attract. And again, as we talked about, no sharing of electrons happening. The other type, obviously, of nomenclature that we're going to talk about involves really covalent bonding, or molecular sort of compounds. That is, as we talked about, between our two nonmetals, and like we talked about with bonding, because they both basically have these similar periodic trends, neither one wants to give away their electrons. So again, we're going to have some type of sharing of those electrons happening here. Again, as we also talked about, either equal sharing, unequal sharing. But those are the two types of compounds we're going to talk about in terms of naming. That is a periodic table, and very bright periodic table as well, lots of colors. We also should remind ourselves that there are certain elements that when they do gain a charge, right, they have fixed types of charges. Also a reminder that if you have an element by itself that's uncombined, not combined with any other element, they don't have charges. So if you just take an element off the periodic table, no charge happening there. Only when really metals and nonmetals hook up, they start getting charges and such. Remember that everybody in group 1 will have a +1 charge, right? Everybody in group 2 will have a +2 charge. Really here, it's kind of aluminum in most cases, will be +3. Occasionally gallium underneath gets in there. Here we have our staircase coming down here where our metalloids are. We do skip group 4, and then we go group 5, which is our nonmetals, and they are going to gain electrons, so -3. Group 6, -2, and -1 for group 7. And once again, we're really talking about over here our nonmetals, right, kind of guys. Remember, you do have to be a little careful in this region, and why there's not really a great pattern for 4, because we have like nonmetals, metalloids, and below the staircase, all these guys that you probably can't even see my circle. All those guys down there are metals, right? Pretty much. Yeah? So we have a combination of stuff. So when we talk about negative charges, those are going to be our nonmetals that are gaining electrons. The transition metals, which are in this region here, they have typically a variable type of charge. There are, though, 3 exceptions to that. And that is right here, this sort of backwards L, if you will. I'm in here. So zinc and cadmium, when it makes a charge, will always be +2. If you hang a leftover there to silver, it will make a +1 charge. So although those 3 are transition metals, they have a fixed positive charge. Everybody else pretty much in the transition metal region. Everybody else in this transition metal region, and as we'll talk about, even outside of that transition metal region, will have actually more of a variable type of positive charge when we're talking about metals. And you'll have to do a little bit extra in terms of the naming when we get to, obviously, those guys. That's another periodic table in case we missed the first one. So let's talk a little bit first off, though, about ions. And when we have ions, there are obviously 2 types that we've been talking about. There are cations, which are positively charged, result of metals losing electrons. These are things that have charges. And we have our anions, which are negatively charged, which again are usually a result of nonmetals gaining electrons. When we go to write formulas for ions, so if you're asked to write the formula for the cation, or you're asked to write the formula for the anion, you should include the charges. So if you had something like H plus, Na plus, Ca2 plus, whatever it may be there. We'll go with Ba2 plus. These are all formulas for ions, which means they all have charges that should be written on them. And for our positive guys, which most of them come from a metal, except for hydrogen there, we pretty much just use the whole name of the element. So this would be known as the hydrogen ion. This would be known as the sodium ion. This would be our calcium ion. And this would be our barium ion. So basically anything that's a positively charged ion, you're just going to roll with the whole name basically of the element. And you can put ion at the end of it because it is an ion. And once again, when you are drawing the formulas of the ions, the charges should be included because if you do not put the charges in there, then it's not an ion, right? So if you're asked to draw that thing. For our nonmetals, which are our anions, O2 minus, Br minus, we got there, go N3 minus. The way that we name ions that are anions here is we take the starting part of the nonmetal name and we drop off some of the end and sometimes a little bit more than the end, and we replace the end part of it with IDE. Yeah, so IDE here. So hydrogen in the negative form, which is one of the only elements that could go both ways, be positive and negative here. Instead of hydrogen, this is known as the hydride, IDE ion. Instead of oxygen, that is known as the oxide ion. So we drop a little bit more than the end there. Instead of bromine, this would be the bromide, IDE ion. And instead of nitrogen, this would be the nitride, IDE ion. So negative guys, drop the last part, IDE at the back end. Positive guys, full name of the element. Once again here, our hydrogen can go both ways. So most of the time, hydrogen will be probably positive. The only time hydrogen will be negative is usually when it comes after a metal. So if it comes after a metal, like LiH, then it will be lithium hydride. It'll be the negative version of it. Other than that, probably a safe bet hydrogen is going to be more of a positive sort of ion. Now, again, when we write the formulas for our anions, which are negatively charged, we do need to include the negative charge along the way. Also really important when we look at a table like this, as you can see there, we have our hydrogen and our lithium and our sodium. Again, just the whole name and our IDE there for our nonmetals. When we do take a ionic compound and we put it together in terms of its formula, the actual ionic compound formula, which should always be made up of a cation and an anion together, and that is always how the formula and also the name should always be written like this. Should always be the positive guy first, followed by the negative guy. We want to make sure that the overall charge here equals 0 when we put it together. And really the reason for that is what we talked about in bonding. The reason for that is it allows all those elements to do what? What happens when they gain and lose electrons? They end up where? They end up like the noble gases. So when we balance out the charges here of our positive ion and our negative ion, what we're essentially doing is allowing all those guys to reach noble gas configuration. And we want to do that in the simplest way possible for our ionic compound. That is why, again, if we took a lithium ion and we took a bromide ion, that is -1 and +1, we just need one of each of those. And this would be the correct formula for lithium bromide. It has no charge, but it is made up of a cation that has a charge and an anion that also has a charge. Same idea, like I think we did this guy when we were doing bonding, when we put our calcium ion together with our fluoride ion. When we put it together, we have +2 and -1. We actually need one more of our fluoride there to balance out the charge. Gives us +2 and an overall -2 happening. And that means we have one calcium and two Fs. And that would be our proper formula for something like calcium fluoride. Again, here it is made up of a cation, that is Ca2 plus. And by the way, if you're asked to write the anion formula for this, it is just F minus. It is not F2 minus or anything like that on the bottom or anything like that. So the actual anion here is F minus only. Any questions on that there? So let's talk about ionic nomenclature when we have a type 1 compound versus a type 2 compound. So a type 1 compound is an ionic compound, which means that you will have a metal and a nonmetal together. And pretty much whenever a metal is involved, it is the most important thing in terms of how you go about naming it. So it's really always the metal. If it's involved, that is really the one that kind of determines how you go about naming this. So what is a type 1 ionic compound? That is where the metal, which again is the most important thing, has a fixed positive charge. So as we just talked about a second ago, that's going to be all of our metals from group 1, 2, 3. That's also going to be zinc, cadmium, and silver. So the nice thing is, as soon as you can identify the metal as being a type 1 type metal, you pretty much could roll right into the naming part. You don't have to figure out anything else other than basically name it. And what I mean by that is the way that we name type 1 is we use the whole name of the metal, or the positive guy, and we use the non-metal name, which is our negative guy, again, dropping off the last part of it and adding IDE to it. So really, when you have a compound in front of you and you want to name it, like if we had our CaBr2, for example, really the first thing that you want to probably figure out if you're not sure is to change the page now. You want to really figure out what you're dealing with. So what I mean by that is calcium is a metal, Br is a nonmetal. So as soon as you identify that you have a metal and a nonmetal happening, that should automatically trigger you to this is an ionic compound. And now really what I want to figure out is it a type 1 or a type 2 that we'll talk about in a second? And as I mentioned before, out of those two, it is always the metal that's most important to help you decide that. When we look on the periodic table for calcium, we see it in group number 2, which means it has a fixed positive charge. And that's all she wrote at that point. That is going to be a type 1 compound. And that's all the information I need to name this. I'm going to go whole name of my metal, which is calcium. And I'm going to go whole name of my Br there with the IDE, which is bromide. So this would be calcium bromide. First off, any questions on that? So let's talk about what everybody wants to do, and they're screaming in your head right now. Shouldn't there be like a prefix because there's a 2 there? Isn't that important? And the answer is no, unless you would like an X. So there is no prefixes here. It doesn't matter if you got 400 of those bromates or 300 of the calciums, by the way. It doesn't matter either. We do not use prefixes here when you have a metal and a nonmetal. So if you have a metal involved and you're using a prefix, you're probably wrong. Yeah, you should never use it. The reason, obviously, the 2 is here is what we talked about before. This is made up of a calcium ion, which is the cation, and it's made up again of a bromide ion, which is the anion. And that too is to tell us that we don't have one of the Br minuses, but we have two of them. It has absolutely no effect on the actual name. And it's a very common mistake that people, when they go name things, they want to put prefixes everywhere because it's more chemistry-like, I guess, if you lay up a prefix or something like that. But there is definitely a place for prefixes. And if you have a metal involved, that is not the place for sure. So you should not really do that. There's really only one place where that might occur, and there's a reason why that is, and we'll talk about it later on, but definitely not here. Any questions on that there? All right, so obviously there's our little table of fixed charges, and these would be all type 1 metals, obviously as well with our zinc, cadmium, and silver would also be our type 1 metals with +2s happening there and a +1 happening there. So why don't you name each of these? Let me swap this one out since I kind of stole the we already did that one. Why don't you do maybe let's do MG. Let's do let's do this. Why don't you do that? Why don't you also write the formula for the following? Why don't you write the formula for sodium sulfide? Why don't you write the proper formula for aluminum oxide? And why don't you write the formula for, and we'll do calcium. We'll do calcium chloride. Why not? All right, so names on the left there, and take a look here, see how we're doing. So again, we have K, which is potassium. That's a metal. Cl is chlorine, which is a nonmetal. So right off the bat, that should tell you you're dealing with an ionic compound. Here we want to focus in on the metal, which is potassium. We can find potassium in group number 1 on the periodic table. So that tells you it's a type 1 compound. And really for naming it, that's all you need at this point. This would be potassium. And again, the chlorine would become chloride. This is made up, obviously, here of a cation that has a formula of K plus and an anion that has a formula of Cl minus, which again is why we only need one of each of those guys when we put it together. Any questions on that one there? Once again, we want to do the same sort of analysis here. So zinc is a metal. Sulfur is a nonmetal. So once again, that's going to be ionic. Zinc is actually a transition metal, but it is one of the three that we talked about that has a fixed charge, which tells us again it's going to be a type 1 compound. Once again, for naming purposes, that's all we need to know. And we're going to use the whole name here of the metal, which is zinc. Our sulfur will get the IDE treatment at the end of it, and this would be zinc sulfide. Once again here, the cation formula is zinc with a +2 charge. The anion formula is S with a -2 charge, as that's group 6 on the periodic table. Also +2, -2, why we only need one of them when we put them together to make the formula. Coming here, we got magnesium metal, phosphorus nonmetal. Once again, tells us it's ionic. We're going to focus our attention on the magnesium, which is group number 2 on the periodic table. Has a fixed charge, tells us it's type 1. That's all we need for the naming. This is going to be magnesium, the whole name. And again, our phosphorus will drop a little bit of the back end or maybe more, and that will be phosphide. Once again, here we have no prefixes, even though we have multiples of each of those things. And again, that's because of the ions that are present. Here, our cation, I'll go over here. Cation here is magnesium with a +2. Our anion here is going to be phosphorus with a -3. And again, those would be the formulas for the anion and cation if you had to write it Again, no such thing as like P23 minus. Yeah. So that is incorrect if you had to write the formula for the anion. Obviously, that's why we have 2 and 3 of those to balance it out to 6, so that when we put it together, we get a basically +6, -6 charge overall. Here we have barium, which is a metal. And remember, our friend hydrogen is really a non-metal, so that's going to still be ionic. Here, barium is group 2, which tells us fixed charge, type 1 type compound. This is going to be whole name of our first guy, and our second guy here going to get the IDE treatment, and this would be barium hydride. Here, the cation would be barium with a +2 charge, and that is a metal where hydrogen comes second, and that is the time where hydrogen will be negative in this case, which is the hydride version of it. Any questions on any of those names there? All right, we're going to put it together. Really going to take kind of the same approach to put it together, with the understanding, obviously, as we've talked about, that we want to make sure we end up with an overall charge of 0 when we put these things together. So first off, when we look at the name here, we got sodium. That's a metal. Sulfide is a non-metal, so I know it's ionic. So really, I just want the basic units of those ions, what they are. So sodium is group 1, which is a +1. Sulfide is group 6, which means it has a -2. Once again, when I put this together, I need to equal 0. That means I do need one more sodium ion there to give me a +2 to balance out the -2 from the sulfur. At this point, if it helps you, you can just count what you wrote. 1, 2 sodiums and 1 sulfur. Yeah, looks something like that. Yeah, will be our proper formula. By the way, sometimes people are taught to let's kind of move charges down and up and stuff like that. And by the way, that works great if you're only good, if you're happy with like 94% of the time. It does not work 100% of the time. So just keep that in mind. If you just blindly move things, you might get the wrong answer a number of times. But if you're good with like 94% of the time, you can just blindly move charges up and down and you'll be all right. But so again, it's better just to think about, again, properly balancing it out so that you do get the correct formula. We have aluminum oxide, aluminum metal, oxygen non-metal, it's ionic. Aluminum is group 3, so we're going to have a +3 over there. Oxygen is group 6, which means it will be a -2. Once again, when we put these guys together, common number is 6 if you multiply those numbers together. That means to get our aluminum to 6, we actually need one more of those guys. And really, to get our oxygen to 6, we need a grand total of 3 of those guys. And once again, that is 2 aluminums and 1, 2, 3 oxygens. And there would be the formula. Yeah. Any questions on that there? Lastly, here we have calcium metal, chloride non-metal, once again, ionic. Here, calcium group 2, going to be a +2, chloride or chlorine, group 7, -1. Once again, when we put these together, we will actually need one more of the Cl minuses. That gives us a +2 to balance out the overall -2 happening on this side. And once again, that is 1 calcium and 2 of those Cls. Any questions on any of those there? So these are type 1 ionic compounds. Again, metal, always the important one here. And what makes it a type 1 is that metal will have a fixed charge. Any questions? Clear, you need to be able to write formulas and name them, right? Then let's talk about type 2 ionic compounds. And type 2 is still ionic. It is still between a metal and a non-metal, and nothing much has changed in the fact that it is still the metal that is the most important one here. The difference between a type 1 and type 2 compound is the type 2 metal has a variable positive charge. So those are going to be your transition metals. And just to the right on the periodic table, underneath the staircase where we have our metalloids. So things like tin, things like lead, things like antimony, bismuth, those guys, they can have a variable charge, even though they technically are not uh, transition metals. They are basically named the same way because they can have that variable charge. So what is the deal with these? We name these very similar to how we name type 1. We use the whole name of the metal, our positive guy. We still roll with the non-metal name that we drop the last part and put the IDE. The additional thing that we put between the two are Roman numerals. And we use Roman numerals to indicate the charge on one cation that you pull out, one positive guy. Not what a lot of people think the Roman numeral means, which is how many metals you have, which is incorrect. It is actually, if you took one of those metals that has a positive charge, what the actual positive charge is on it. So, for example, if we had our friend here, FeCl2, we see iron, which is a metal, chlorine, which is a nonmetal, which tells us it is ionic. Once again, the metal is the most important guy, and we do see iron dead center in the transition metal region. And that should automatically tell you probably a variable type of charge. So we need to figure out what the charge is. The good news is you will always know the charge on whatever it's attached to. So in this case, we have one iron ion, but we do have Cl, which is group 7 and -1, and there are two of them. That means that overall we do have a -2 happening here. So to balance out the negative with the positive, our one iron will has to carry a +2 charge. That means that this name here will be iron Roman numeral 2. And again, the 2 is for our charge on one of those. And again, the back end here will be chloride. Once again, no prefixes as well, because a way to remember that is I see a metal, so probably not a great idea. So we do not want to use a prefix in this particular case. Same idea here. Doesn't matter if you got a bunch of them or one or two of these guys. It will have no effect on the name in terms of any need for prefix. The reason we do need to use the Roman numeral with type 2 compounds is we could have, for example, FeCl3. And in this case, what we got going on is Fe, which is definitely still our transition metal. But now we have 1, 2, and 3 of the Cl minuses. That gives us a grand total of -3. That means in this case, our iron actually is the iron with a +3 charge. And that means that this guy's name would be iron Roman numeral 3, again, because of the charge, and still chloride. So really naming is all about telling people, hey, in the first case, we're talking about the iron that has a +2 charge. Ooh, good catch. And in the second case, we're talking about the iron that has a +3 charge. The reason we do not need Roman numerals for the type 1 is that is the only charge they can have. So you should know that is basically the idea there. So we don't have to tell you that, sodium has a +1 charge because that is the only charge it can have. It has a fixed charge, so you do not need to include that in the naming. And you should not include it in the naming. Any questions on that there? So here's a lot of our transition metals. And one of the ones that sometimes, and again, these guys are more type 1 guys here in this area here. So these are really type 1. Everybody else is going to be type 2. And again, you can see out here, just to the right of the transition metal region, we have ones that will also be a type 2. The one that sometimes confuses people is our friend here, mercury. That is Hg22 plus, and that is Hg2 plus. And oddly speaking, the one that has all the twos is actually mercury 1. And the one that has only 1 2 is actually mercury 2. And that is because this is what's known as a dimer. It's actually two mercury 1s stuck together, which is why there's a 2 on the bottom, because there's two of those guys basically stuck together. And each one has a +1 charge, and it will be overall +2. Yes. Any questions on that there? So how do you know if it's really the +2 or +1? That 2 will usually hang around the bottom 2 I'm talking about. So for example, if I roll with like this, very badly there, versus this guy here would be mercury 1 or 2. It'd be mercury 1, as that 2 is still there that we see here, right? This second one would actually be mercury 2. No 2 on the bottom. So that mercury 1 will typically still have that 2 on the bottom. This is basically mercury 1 and oxide with the -2, which is why you just need one of each of those. But this 1 comes as a 2, basically. So that's why the 2 stays there. This is Hg2 plus and O2 minus. Also only need 1, but this comes as a 1 instead of a 2, like the kind of first guy there. So mercury is a little weird in that sense. But again, the one with all the 2s is actually 1, and the one with the less number of 2s is actually the second one there. Any questions on that there? There's also a older way of naming, which clearly this is just messed up. So that's a really bad hand up. But I think it looks all right on yours. But the good news is we're not going to use sort of the older naming way. The older naming way is they actually don't use Roman numerals, but you use kind of like the old school name. So like cupric and cuprous are ferric and ferrous. That would be copper 2, copper 1, not copper, iron 3, and iron 2. So the old way of naming is kind of the old school name, and it either ends in ick or us. The one that ends in ick is the one that has the higher positive charge, and the one that ends in us, OUS, is the one with the lower positive charge, and that's sort of old school name. You can remember that you know, you feel icky because you ate too much. It has the higher sort of charge in that sense. But we will not use that. We will strictly use Roman numerals here for type 2. But I will say these four examples actually still pop up a lot in like literature and stuff like that. So people kind of still use those occasionally in literature and stuff like that. So if you see it, that's basically what it refers to. All right, so why don't you name these guys here? Let me give you maybe some to write the formula. So why don't you do actually, why don't you give the name for this one too? And why don't we do let's do chromium for oxide. Actually, no, let's do chromium for bromide. That's what I want to do, I think. Let's do bromide on that one. Let us do let's do copper to nitride. Let's do nickel for phosphide. All right, so let's do names on the left there and formulas on the right. Here at these. So again, we're going to take the same approach. That is cobalt, which is a metal. That is chlorine, which is a non-metal. So once again, that ticks off the box of ionic. Our metal, the important one, which is cobalt, which we can find in the transition metal region, which again will tell us that it is a type 2. So we do need to figure out the charge. So once again, cobalt does not have a charge that maybe we know, but we do know that Cl is -1, and there are 3 of them. That gives us a -3 overall, which means this needs to balance out to +3. Again, whole name of the first guy, which is our cobalt, Roman numeral 3 for the charge, not how many we have. And regardless of how many of these we have, they are still going to be called chloride. Any questions on that one there? Coming next, we have Cu, which is copper, metal. I is iodine, non-metal. Again, going to be ionic. Copper also there in the transition metal region tells us it's going to be a type 2. So we do need a Roman numeral. In this case, we have just one copper. We do know that I is group 7, should have a -1 charge. So to balance that out, it has to be a +1 charge on the copper in this case. And that's going to give me copper, once again here, Roman numeral 1 and iodide. Any questions on that one there? Here we have tin, which is a metal, Br, which is a non-metal, so that tells us it's ionic. And again here, tin is actually not a transition metal, but it is one of those ones to the right that's below the staircase, which is basically still a type 2 metal. And that means that tin, not sure maybe what the charge is, but we do have 4 of these Brs, each from group 7, which means if you want to draw them out, you can. That's going to be a -4 happening there for our negative side. Going to balance out our positive there with a +4, and that will give us 10 Roman numeral 4, and once again, bromide here for our charge. Any questions on those 3 there? Last one here is, I don't know, that is lead and oxygen. So that's ionic, metal, non-metal. Lead again to the right of the transition metals, but underneath the staircase. So it will have variable charge. So in this case, we have 1 lead. We have oxygen with a -2 charge, and there's 2 of them. That is a -4. That means that's a +4 and not lead 2 like probably half of you have on your paper right about now. That is lead Roman numeral 4 oxide. And this would be a prime example of one where you would not get it correct by just flopping the numbers up and down. Yeah. So again, 94% of the time it works. Mathematically figured out. So make sure you know how to do it correctly. Lead Roman numeral 4. Question on that one there. All right, to finish these 3 here, just to finish this little part, chromium Roman numeral 4 is really great because that tells me chromium has what type of charge? +4, right? So nothing to figure out there. Bromide is group 7, which has a -1 charge. So once again, we need to balance that out. So we're going to need, again, a total of 4 of these guys. And that's going to give me a CrBr4 happening here to balance it out. Once again here, copper Roman numeral 2 tells me it's definitely type 2 because I got a Roman numeral happening. Also tells me copper has a +2 charge because of that. Nitride is nitrogen, which is group 5 and has a -3 charge. Common number between these 2 is 6. So to get my nitrogen to 6, I need 2 of them. To get my copper to 6, I need 3 of them. And again, you can count them 1, 2, 3. So that is a copper with 3. And 1 and 2 of those. So that's a nitrogen. And there it is. Yes, so we have our name and our formula. Lastly, same deal here. We got Roman numeral 4. That tells me my nickel is carrying a +4 charge because of that. Phosphide there is group 3 as well, which is a -3. There I say a 12 looks like a common number there. So to get my phosphorus to 12, I need actually 4 of those guys, right? And to get my nickel to 12, I need 3 of them. And that's going to give me an Ni, and there are 3. And there are 4 of these guys. And we will end up with a formula that looks something like that, yeah? Any questions on type 1 or type 2? All right, we'll lay it up there.